Last day we started surface tension, and I explained why these liquid surfaces behave as some kind of elastic membrane, why they show some kind of elastic membrane characteristics, and I explained the reason behind that. So when I was explaining that reason behind surface tension of a liquid layer, mainly I said three important keywords. First important keyword is, you can remember that, sphere of influence. Then molecular range. Next one is surface film. Don't worry, I will again give a small brief explanation about what we discussed last day, and I continue today's session. And after explaining why liquid surfaces obtain this elastic membrane, this characteristic, and we started to define what is surface tension coefficient, and then we discussed about surface energy, a relationship between surface energy and surface tension, and we stopped from that. I think we did few questions. Okay, but today the plan is to discuss remaining thing. Now, first important thing is intermolecular forces. Intermolecular forces we can divide into mainly two subcategories: cohesive forces and adhesive forces. So what is the main difference between cohesive and adhesive forces? Cohesive forces means intermolecular forces, if not attraction forces, between homogeneous particles. Between two water particles, attraction forces homogeneous. Adhesive forces means that is also kind of intermolecular forces between non-homogeneous particles. For an example, attraction forces between liquid particle and gas particle. For an example, water particle and air particle. That's what we call as adhesive forces. Then I explained surface tension means some kind of result of this cohesive and adhesive forces, right? Then I think I took a longer time and I explained how these liquid surfaces obtain that elastic characteristics, how they behave as that elastic membrane, how liquid surfaces behave as elastic membrane. I took time and explained. So roughly, I'll remind that again. We talked about sphere of influence, right? If you consider liquid particles, specifically liquid particles, then I defined what is sphere of influence. Okay. Then I told you that liquid particles are much deeper in the liquid. Sphere of influence is perfect sphere, result in attraction force acting in that selected particle, always a zero. But I told you that when the liquid particles closer to the liquid surface, those liquid particles sphere of influence are not perfect spheres. Do you understand what I'm saying? Right? For an example, right. For an example, let's say this is my liquid surface. Now, if I select a liquid particle much deeper in this liquid, for an example, this liquid particle is a particle. Then I told you that if I draw the sphere of influence. Now, I think you guys can remember what is the sphere of influence. Sphere of influence means the basic idea is cohesive forces means attraction forces between homogeneous liquid particles. Then all the liquid particles will exert attraction forces, if not cohesive forces, on this liquid particle. But I told you that if I measure a distance equal to molecular range, if I measure a distance equal to molecular range, liquid particles beyond that molecular range, even though liquid particles beyond that molecular range measured from liquid particle A, those liquid particles, even though create attraction forces on particle A, we can neglect it. Because I told you that attraction force is directly proportional to 1 over r square. R means distance between those two particles. If the particle is more away from particle A, attraction force produced by those particles on particle A can be neglected. That's the idea. So therefore, understand, we define a distance called molecular range. Simple R means molecular range. Then I explained that if I create a sphere taking simple R, if not taking molecular range as the radius from particle A, and if I create a sphere, that imaginary sphere I call it as sphere of influence. I call it as sphere of influence. Okay. Sphere of influence. Then I told you that liquid particles inside the sphere of influence will create significant attraction force on particle A. Then I told you that liquid particles away from the sphere of influence, even though they create a force on particle A, we can neglect it. And the summary is, a sphere of influence means, by the name you can understand, sphere of influence means the region where particles spread and region where particles located which can produce significant force on selected particle. That's what we call a sphere of influence, right? So if I consider liquid particle much deeper in the liquid sphere of influence, this is a perfect sphere. Then I told you that resultant attraction force on this particle is 0. But you want to understand, if I select a particle closer to the liquid surface, I told you that if I draw the sphere of influence of this liquid particle, then we could understand that if I draw the sphere of influence of this liquid particle, sphere of influence of this liquid particle, then we can say that it's not a perfect sphere. Am I correct? As a result, I told you that there is some kind of resultant attraction force acting on liquid particles closer to the liquid surface in the down direction, right? Because I told you, now just think about a liquid particle on the liquid surface. Then air particles attraction forces on this liquid particle can be negligible comparing with attraction forces produced by the liquid particles on this liquid particle. So as a result, when you consider this liquid particle, there will be some kind of resultant attraction force acting on this liquid particle in downward direction. So there is some kind of resultant attraction force acting on this liquid particle downward direction. Okay. So then the summary is liquid surfaces, liquid particles closer to the liquid surfaces undergo some kind of resultant attraction force in downward direction. Okay. If I consider the range, if I measure the distance from the surface, simple R distance, in between the simple R range, liquid particles in between the surface and this level, all the liquid particles undergo some kind of resultant force, right? So this is the reason behind surface tension. Okay, then I explained that idea. And lastly, we learned about what is surface tension also. Okay, now we'll continue today's lesson. Today we'll continue. Right. Today, yes. Right. Surface tension, I think we defined what is surface tension. But anyhow, again, I will explain what is surface tension and coefficient of surface tension. Both are same. Put your main topic surface tension slash coefficient of surface tension. Surface tension, if not coefficient of surface tension, both are same idea, right? Topic is surface tension, if not coefficient of surface tension. Inside the bracket notation is capital T. Okay. Now we know these liquid surfaces behave as some kind of elastic membrane, like a rubber. Think about rubber balloon. So when we inflate the balloon, how these rubber balloon stretches, very similar manner, liquid surfaces also stretch in that way. Okay. Now surface tension. Now idea is very simple. Now hereafter understand liquid surfaces are acting as some kind of surface of a balloon. Do you understand? So if you touch a balloon surface, what would happen? It stretches. Very similar manner, liquid surface also behave in that way. Okay. Now, if you think about a liquid surface, this is some kind of liquid surface. Okay. Liquid surface. It's my liquid surface. Right. Now I'm looking from the, now this is a top view. Now I'm looking this liquid surface from the top. And if I draw an imaginary line, then you need to understand this liquid surface acting like an elastic membrane, right? In that case, if I draw an imaginary line on this liquid surface, you want to understand this liquid surface is stretched, right? Liquid surface is stretched. So therefore, if I ask you, what is the resultant force acting on this imaginary line, your answer must be 0. The reason is tension force acting along this imaginary line, acting in both directions. Tension force acting on this imaginary line, act in both directions. Therefore, resultant tension, for resultant force acting on that imaginary line is 0. So therefore, that's why they define, I think you can remember how we define surface tension. That's why they define surface tension only considering tension forces in one direction, right? So how they define, write down. First of all, we'll define like this. Length of, when I consider this imaginary line, length of this imaginary line is 1 meters. 1 meters. Then I'm considering only one direction. But if I draw an imaginary line, understand tension forces act on both directions. Resultant tension force acting on this imaginary line is 0. How I define surface tension? If I consider 1 meter long imaginary line on this liquid surface, the resultant tension force acting perpendicular to that imaginary line only through one direction, only in one direction. Resultant tension force acting on this 1 meter imaginary line perpendicular to imaginary line only in one direction, we call as resultant, if not we call as surface tension. Do you understand? Surface tension, capital T, the resultant tension force acting in one direction, perpendicular to line, right? So therefore, write down the definition is, you know this diagram also. Surface tension of a liquid is defined as, surface tension of a liquid is defined as the force acting along the surface, the force acting along the surface of the liquid, on a unit length, of an imaginary line drawn, on the surface of the liquid, comma, normal to end towards one side of the line, Please highlight. Along the surface, unit length, imaginary line, normal to towards one side. Then what is the units of surface tension? Simply surface tension means understand tension, resultant tension force acting per unit length. Because you considered 1 meter long imaginary line of the surface, resultant tension force acting on that 1 meter long imaginary line in one direction. So therefore, surface tension means we can say force per unit length. What is the unit of surface tension? Units of surface tension is I can say that Newton per meter, force per unit length, right? Therefore, surface tension has a unit of newtons per meter. Newtons per meter. So there is another unit also, kilograms per square second. If not, kilograms is minus 2. And if we find the dimensions of surface tension, dimension of surface tension, dimensions, dimensions of force over dimension of length, right? Dimension of forces, we know that MLT minus 2. MLT minus 2. Dimension of length is capital L. Then we are getting MT minus 2. Dimensions of surface tension will be MT minus 2. MT minus 2. Now write down subtopic surface tension force inside the bracket capital F. Now we know what is surface tension. Always understand surface tension means a resultant tension force acting on imaginary line of 1 meter length in one direction. A surface tension force. Write down surface tension force. Surface tension force. Capital F. Write down if capital F is the total force acting. If capital F is the total force acting, normally on an imaginary line of length simple L. Normally on an imaginary line of length simple L to one side of it. And then we know that, right? For 1 meter length, resultant surface tension force is how much? For 1 meter length, resultant surface tension forces, that's capital T. Then for simple L length, surface tension force is capital F. What is the relationship between surface tension force acting on simple L length? 1 over simple L equals T over F. I can write down F equals T into simple L. F equals T into simple L. This idea. I think you guys know that idea also. Now red color pen write down important. Red color pen write down important. Important. Surface tension of a liquid depends on. Surface tension of a liquid depends on the temperature of the liquid and the temperature of the liquid and the medium in contact with the liquid surface. The medium in contact with the liquid surface. Highlight temperature, liquid, different highlighter, highlight, medium in contact with liquid surface. Now sometimes we think that surface tension of a given liquid, because liquid to liquid, obviously surface tension is different. Comparing with water and coconut oil, obviously liquid surface tension is different values. That's true. Even same liquid with the temperature, surface tension will be different. That's okay. Let's say water, even temperature is constant at room temperature 30 degrees Celsius. When you consider water, even you maintain same temperature when you pour water to different vessels made with different materials. Let's say initially you poured the water to a glass vessel. Then you are pouring the same water to a plastic container. Depends on the material that we use to manufacture the container, then also surface tension of the liquid can be different. So therefore, that's also some kind of important point you want to notice. Right. Now subtopic, Behavior of surface tension with temperature. Now subtopic, behavior of surface tension with temperature. Write down. Now, normally what's happening when temperature rises, surface tension decreases. When temperature rises, surface tension decreases. Write down. As the temperature increases, comma, the surface tension rapidly decreases. The surface tension rapidly decreases. Different color pen, no, not red color pen, different color pen, write down. The temperature at which surface tension is zero. The temperature at which surface tension is zero is called critical temperature. Is called critical temperature. Highlight critical temperature. Highlight critical temperature. And now if I do the variation of surface tension with the temperature, now y-axis represents surface tension capital T. My x-axis represents temperature. This time I use theta to represent temperature, because if I use capital T, surface tension also capital T, temperature also capital T, theta. So then the variation would be something like this. When surface tension of a liquid becomes zero, this temperature we call as critical temperature. Critical temperature. Right. Now subtopic, shape of free surface of a liquid. Shape of free surface of a liquid. This is a very important thing. Shape of free surface of a liquid. Write down under that topic, write down. If you carefully observe the free surface of a liquid, in a vessel, not in a container, comma, you can see that the free surface is often curved. The free surface is often curved near the wall of the vessel. Near the wall of the vessel. Near the wall of the vessel. This behavior of a free liquid can be explained in terms of intermolecular forces as follow. Highlighter, free surface, curved near wall, intermolecular forces. Free surfaces, curved near wall, intermolecular forces. Now very carefully listen, this is very, very important idea. It's very important. Now we might have seen that. Now, especially just think about what we call test tubes. And especially we can see this phenomenon when the container have smaller cross-sectional area. For an example, best example is test tubes. Now, just think when you fill a liquid, it can be water or it can be any liquid. When you fill liquid in a test tube, or if not especially in capillary tubes, so you might have seen that these liquid surfaces won't be a flat liquid surface. The meniscus I'm talking about. Liquid meniscus won't be a flat meniscus. So most of the liquids, that liquid meniscus would be some kind of the shape of concave. Some liquids that meniscus would be in a shape of concave. Now I'm going to explain why, rather than it stays as a flat surface, flat meniscus, why they become some kind of convex concave shapes by considering intermolecular forces. Very carefully. Now, this is my container surface. Okay. Right. My liquid surface. Now, very carefully listen. It's very important, very carefully listen. Right? Now, I'm considering a liquid particle which is on the liquid surface, name as A. I name this particle as particle A. It's a liquid particle. This is liquid particle A. Liquid particle A. This particle is a liquid particle on the surface of this liquid. And if I draw the sphere of influence of this liquid particle, if I draw the sphere of influence of this liquid particles, sphere of influence of this liquid particle, sphere of influence. Sphere of influence. Okay. Name of this liquid particle is particle A. Now I drew the sphere of influence of this liquid particle A. Right? Now, if I divide, now the sphere of influence is a perfect sphere. But I can't draw a sphere here because it's a 2D whiteboard. Therefore, understand this is not a circle, it's a sphere. Right? Then, my question is, if I divide the sphere of influence into 4 sections, we can clearly see that this section completely covers with the liquid, this portion. When talking about this section covers with the air particles, this section covers with the solid particles. Am I correct? It's a solid. A solid. It's liquid. It's solid. In this case, if I ask you that, now this is particle A, liquid particle A. If I ask you that, what is the resultant attraction force on liquid particle A by the liquid particles in the sphere of influence? What is the direction of resultant attraction force on particle A by the liquid particles inside the sphere of influence? Liquid particles in this region. What is the resultant attraction force acting on particle A? That must be FL, exactly 45 degree from the vertical direction. If you have a good understanding, you will understand what I'm saying. Right? FL. FL. FL is what? The resultant attraction force on particle A by the liquid particles in the sphere of influence. Now comparing with the attraction force produced on particle A, comparing with attraction forces produced by liquid and solid particles on particle A, attraction force produced by air particles on particle A can be negligible. So therefore, we don't consider any resultant attraction force on particle A by the air particles because, right? Then if I ask you, just think about this portion. What is the resultant attraction force on particle A by the solid particles in this region? Again, that is also 45 degree from the vertical. I don't know the magnitudes. I just say that is Fs. Fs. Then very similar manner, resultant attraction force on particle A by the solid particles in this region, that is also Fs. Now depends on the magnitude of Fs and Fl, the shape will be determined. Do you understand? The shape of the liquid meniscus would be determined depends on the magnitude of Fl and Fs. Okay. If I don't now, what is the resultant of Fs and Fl? Fs, Fl both are in the same line. What is the resultant of Fs and Fl? I will say Fl minus Fs. It can be Fs minus Fl also. I say it as Fl minus Fs. Depends on the magnitude. It can be different. If I draw it a bit larger, same diagram. If I draw it a bit larger. Okay. Okay. Then solid liquid. Solid liquid. Now, when I consider Fs, Fl, resultant of Fs and Fl, I will say that in this direction, Fl minus Fs, right? This one will be Fl minus Fs. And this one is Fs. 45 degree, 45 degree. Okay. Fs. Now, depends on the magnitude. Now, understand force the vector. These are vectors. It depends on the magnitude of which force is larger. Fs larger or Fl larger. Based on that, the shape of the liquid meniscus will be determined. After you drew these two diagrams, write down red color pen important. Red color pen important, write down. Important, very important. The shape of the liquid surface would arrange. The shape of the liquid surface would arrange always normally to the resultant force acting on it. Always, normally on the resultant force acting on it. Next point also red color pen. If not, a component of this force will act parallel to the liquid surface. If not, a component of this liquid force will act parallel to this liquid surface, causes a motion. Right. Now I'm going to decide. This is my liquid surface. I'm going to decide what would be the shape of this liquid surface, liquid meniscus. Case number one. Case number one. Case number one. F is larger than Fl minus Fs. Fl minus Fs. Case number one. If this happens, what would be the resultant? Look here. Okay. Now there are two forces, Fs FL minus Fs. Now very carefully understand. Now just think that suppose if F is larger than FL minus Fs. Now angle is 45, 45. If this one is larger vector, what is the direction of resultant vector? Your resultant vector would be like this. Your resultant vector would be closer to Fs. Do you understand? In that case, now F is larger than FL minus Fs, then resultant will be inside the solid this direction, right? And now this is your liquid surface. This is your liquid particle A. This is your liquid particle A. Liquid particle A. What is the resultant force acting on the liquid particle A? Resultant force acting on liquid particle A is this direction. This direction, resultant. Next important thing, always understand, always liquid surface must be arranged perpendicular to the resultant force acting on the liquid particle. Very important condition, always liquid surface arrange perpendicular to the resultant force acting on the liquid particle. This is the direction of resultant force acting on the liquid particle. Then liquid surface must be arranged perpendicular to it. Perpendicular to it. In that case, perpendicular to it. Perpendicular to it. The perpendicular line. Perpendicular to it. Then your liquid surface would be. Then your liquid surface would be something like this. Liquid surface must arrange perpendicular to it. Am I correct? This is how your liquid surface must be arranged. Do you understand? Now draw this diagram. Then it is some kind of concave. This is some kind of concave meniscus. Concave meniscus. Some kind of concave meniscus. After you drew these two diagrams, you are liquid. These are liquid. Now write down. Here the resultant attraction force. Here the resultant attraction force on liquid molecule A. On liquid molecule A should be closer to Fs. Should be closer to Fs. This diagram concave. That is resultant force acts towards. Write down. That is resultant force acts towards the wall of the vessel. That is resultant force acts towards the wall of the vessel. Then meniscus makes a concave shape. Then meniscus makes a concave shape. Highlight resultant force towards wall, meniscus concave shape. That's the idea. Case number 2. Case number 2. What would happen if Fs exactly equals to FL minus Fs? FL minus Fs. Now, Fs vector and FL minus Fs vector both are equal means what is the direction of resultant force? Vertical downwards. Direction of resultant force acting on this particle A. Direction of resultant force acting on this particle A is vertical down direction. In that case, how would be this liquid surface arranged? If I draw it. If I draw it. In that case, this is my liquid particle. Now my resultant force acting on the liquid particle is vertical down direction. Resultant. I told you that always liquid surface will arrange perpendicular to the resultant force acting on the particles. Then how would be your liquid surface? Liquid surface would be exactly horizontal. Exactly horizontal. Write down the resultant force of attraction on liquid molecule A. The resultant force of attraction on liquid molecule A acts downwards along the wall of the vessel. Acts downwards along the wall of the vessel. Now, case number 3. If F is smaller than case number 3. Case number 3. F is smaller than FL minus Fs. FL minus Fs. In that case, now we know this time FL minus Fs is larger. What is the resultant direction of the resultant force? This way. Then if this is your particle A, this is your particle A, resultant direction will be towards the liquid. Result. Then your liquid surface must be arranged perpendicular to the resultant force, right? Your liquid surface must be perpendicular to the resultant force. Perpendicular to the resultant force. Perpendicular to the resultant force. Then how would be your liquid surface? A liquid surface would be like this. Especially mercury, liquid like mercury. Okay. Right. Now write down. Here the resultant attraction force on liquid molecule A. Here the resultant attraction force on liquid molecule A should be hello? Right. I hope you can hear, right? Should be closer to FL minus Fs. Should be closer to FL minus Fs. That is, resultant force acts towards the liquid. That is, resultant force acts towards the liquid. The meniscus makes a convex shape. 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 Now, I hope you guys understand why some liquid surfaces, liquid meniscus, they are like concave shapes, why some liquid meniscus are in the shape of convex, why some liquids are flat. I hope you guys understand. Then next important thing we want to learn is angle of contact inside the bracket theta. Main topic, angle of contact inside the bracket theta. Write down red color pen, important. At a point where a free liquid surface, meets a solid wall, meets a solid wall, meets a solid wall, comma, the angle made by the tangent drawn to the free liquid surface. The angle made by the tangent drawn to the free liquid surface with the solid wall. The angle made by the tangent drawn to the free liquid surface with the solid wall is measured through the liquid. Is measured through the liquid. Is measured through the liquid, comma, it is called angle of contact. It is called angle of contact. Highlight angle, tangent, free liquid surface with solid through liquid. With solid through liquid. Right? Now we know convex, concave, ni flat. Angle of contact. Angle of contact. Theta. In this case, This is my solid wall, right? Let's say this is my liquid surface. This is my free liquid surface. Liquid surface. The liquid surface. Now, what is this angle of contact? Angle of contact means they have mentioned tangent drawn to the free liquid surface with the solid wall. Now, this is the liquid surface which touches the solid wall. This is the liquid surface which touches the solid wall. If I draw a tangent line, if I draw a tangent line to the liquid surface which touches the solid wall, my tangent line, am I correct? Tangent line. Tangent line. Free liquid surface, again here, angle made by the tangent drawn to the free liquid surface with the solid measured through the liquid. Now, this angle must be measured from solid to the tangent line. Angle must be measured from the solid to the tangent line. Here is my tangent line. This is my solid. This is my tangent line. This is my solid surface. Angle must be measured from solid to the tangent line through the liquid. That's important. Right? Then one can measure in this way, right? One can measure the angle this way. But that's wrong. We want to measure always angle between the solid and the tangent line through the liquid. Then this angle we called as angle of contact. This angle we call as angle of contact theta. Right. So if we find the angle of contact for a convex liquid surface, draw a tangent line for the liquid surface which touches the solid. Tangent line. Tangent. Then start measuring the angle from the solid to the tangent through the liquid. Solid to the tangent line through the liquid. Measure the angle from solid to the tangent through the liquid. This angle is we call as angle of contact. What can you say about the angle of contact for a flat liquid surface? If the liquid surface is flat, then what can you say about the angle of contact for a flat liquid surface? Liquid surface, flat. In that case, solid to, if I draw a tangent line to the flat surface, angle is always 90. Have you guys understood what I'm saying? Then I hope you guys understood up to now. Everything is, I hope you guys understood up to now whatever I explained. Okay. Now write down important point. When the angle of contact is 0, right? Important point. When the angle of contact is 0, inside the bracket O very small, inside the bracket O very small, close the bracket. It is said that the liquid weights the solid. It is said that the liquid weights the solid. And when the contact angle is larger, when contact angle is larger, it is said that the liquid does not weigh the solid. It is said that the liquid does not weigh the solid. Highlight angle of contact 0 or very small. Highlight angle of contact 0 or very small liquid wets the solid. Highlight, contact angle larger, liquid does not wet the solid, right? Okay. Now I think you understood how this angle of contact is measured. Now here we drew for concave liquid meniscus and convex liquid meniscus. How would we measure angle of contact? And I told you that for a flat liquid surface, angle of contact would be a 90. Now quickly draw a diagram. Quickly draw a liquid surface which has 0 angle of contact. Just think there's a solid wall like this. Just try to draw liquid surface which has 0 angle of contact. Draw it quickly. If you draw it, you would obtain something like this. Now, 90-degree angle of contact means flat liquid surface. Then how would we draw 0-degree angle of contact liquid surface? This is a solid wall. Okay. This is a solid wall. Then if you draw it, if the liquid has 0-degree angle of contact, this is how your liquid surface would be. Do you understand? Your liquid surface is like this. Like this. So angle of contact is 0. Angle of contact is 0. Theta equals 0. Okay, theta equals 0. Angle of contact is 0. Now you know how to draw when the angle of contact is 90. We know liquid surface is perpendicular to the solid wall. You know that one. This example shows that angle of contact is 90. That means the liquid surface is flat to the solid wall. Okay, right. Important, write down important color pen. Angle of contact depends on both container and liquid. Angle of contact depends on both container and liquid. Now only most important thing which will important to do the questions. Now you know what is this angle of contact. Now we know what is the surface tension. Surface tension means some kind of elasticity, some kind of tension acting on the liquid, right? Okay. Now put your main topic. Case 1, if the angle of contact theta is 0. Case 1, if the angle of contact theta is 0. If the angle of contact theta is 0. Right. Now surface tension means attraction force on attraction in liquid surfaces, right? Okay, when the angle of contact is 0, now as I mentioned before, look here. Now every action has equal and opposite reaction, right? Now angle of contact is 0. This is my solid surface. Let's assume in that way. Now there's a liquid. Now very carefully understand what I'm saying. Very carefully understand what I'm saying. Now, if we mark the surface tension force on this liquid surface, how would you mark? Surface tension force on this liquid surface and surface tension force on the solid wall. That's the important idea. A surface tension is also some kind of force. I want to mark surface. Now what happens is my solid. This is my solid liquid surface. Solid surface. Solid surface. Liquid surface. This is liquid surface. It's liquid. Liquid surface. If I ask you to mark surface tension force on the liquid surface, how would you mark? Now what happened? So when we place this liquid in this container, what happened? Now we expect liquid surface would be flat, but what happened? This liquid surface has become in this concave shape. It seems like someone is pulling the liquid in both sides. Am I correct what I'm saying? Right now, when we pour this liquid, it obtains some kind of concave shape. It seems like someone is pulling the liquid towards the solid, right? It seems like someone is pulling the liquid towards the solid. Now, what is the direction of surface tension force acting on the liquid? Direction of surface tension force acting on the liquid is, very carefully understand, along the surface upwards. Along the surface upwards. Along the surface upwards. Along the surface upwards. What is capital D? Surface tension on the liquid. On the liquid. Surface tension on the liquid. Surface tension on the liquid. On the liquid. Right? Now, every action has equal opposite reaction. When liquid, when surface tension force is exerted on the surface of the liquid along the surface upwards, equal surface tension force acting on the solid along the surface downwards. What is this T? Surface tension acting on the solid. Surface tension acting on the solid. Very carefully understand, it's very important. Surface tension. Surface tension on the solid. Do you understand? If the angle is theta, this angle is the angle of contact means over tangent line, measure the angle from the solid to the tangent line. Angle of contact will be theta. Now we are not interested with surface tension on the liquid. We are not interested surface tension on the liquid. Now we are interested surface tension on the solid. Now my question is, if the theta is 0, very carefully listen. If the theta starts measuring from the solid to tangent line, theta starts measuring from the solid to tangent line. If the theta is 0, what can we say about the direction of surface tension on the solid? Vertically downwards. Am I correct? If theta is 0, am I correct? If theta is 0, what can we say about the direction of surface tension on the solid? Direction of surface tension on the solid will be vertical downward direction. Surface tension will be vertical downward direction. You got it? Right? Okay. I'll draw this diagram, this one. Draw it quickly. Simply, now case 1, when the angle of contact is 0, write down simply. When rectangular object of cross-sectional, when the rectangular object of cross-sectional length and width, simple A and simple B. Cross-sectional length and width, simple A and simple B, is partially submerged in water. Now, what we are going to do, we are going to find the resultant surface tension force acting on the solid. That's the idea. Suddenly, you don't understand what I'm saying, but when I explain, you will understand. Now, my goal is to find the resultant surface tension force acting on the solid, right? Always understand surface tension forces acting on the solid. Now, surface tension, now understand the first important thing is surface tension forces are exerted only on the surfaces, right? For an example, if there's a liquid, if I dip this marker in the liquid, surface tension forces exerted on the marker. Very careful understand. If I dip this marker into the water in a liquid, there will be surface tension forces exerted on the marker in the area on the marker which touches the surface of the liquid. Surface tension forces are acting only on the surface of the liquid. Do you understand? If I did this marker into the liquid, there will be surface tension forces exerted on the marker in the region where this marker touches the surface of the liquid. Now, what is the region? If not, what is the length? The length which touches the liquid surface, the perimeter, if not, it's a cylinder, the circular length. That means 2πr. Do you understand what I'm saying? Okay, now this time they are telling about something about rectangle scenario. If I draw the diagram for your understanding, if I draw it simply, if I draw the diagram, if I draw it, the liquid which touches the rectangular object. This is the liquid surface which touches the rectangular object. Liquid surface which touches the rectangular object. Now, first important thing is understand surface tension forces act. Surface tension forces act on the solid only along the length of the solid which touches the liquid surface. Surface tension forces act on the solid only along the length of the solid which touches the liquid surface. Then, if I dip this rectangular shaped object into the liquid surface, you can clearly notice what is the length of this object. What is the length of this object which touches the liquid surface? The perimeter, this length, the perimeter of this rectangular length, this perimeter length only touches the liquid surface, right? If suppose if this liquid has zero angle of contact, what is the direction of surface tension acting on the solid? Downward direction. Am I correct? If the angle of contact is zero, direction of surface tension will be downward direction. Then what will happen along this length of the solid which touches the liquid surface? There will be surface tension forces vertical downwards. Only along the length of the solid which touches the liquid surface. No matter how much you dip into the solid, that does not matter. Surface tension acting only the length of the solid which touches the liquid. Then my question is, what is the resultant surface tension force? What is the resultant surface tension force acting on the solid? Now they mention this length is simple A. If I say this gap is simple A and simple B, length and width is simple A and simple B. Simple A, this gap is simple B. Is simple B, simple A. What is the total length of this solid which touches the liquid surface? 2 simple A plus 2 simple B. Surface tension means tension force acting per unit length. Total length of the solid which touches the liquid surface is 2 simple A plus 2 simple B. Then there's a resultant surface tension force acting vertical down direction. There's a resultant surface tension force acting vertical down direction. Capital F equals 2 simple A plus simple B into capital T. I hope you guys understand. Suppose if there's a solid cylinder, if you dip solid cylinder into that liquid, solid cylinder of radius capital R, if you dip into that liquid, if the angle of contact of the liquid is 0, what is the resultant surface tension force acting on the solid cylinder? In this case, if I dip a solid cylinder into the liquid, if I ask you that, what is the length of the solid cylinder which touches the liquid surface? It will be the perimeter, if not circumference, of this cylinder. Then there will be surface tension forces exerted vertical downwards along the perimeter of the solid cylinder. Then what is the direction of resultant surface tension force acting? What is the direction of resultant surface tension force acting on the solid cylinder? Vertical downwards. That is equal to what? What is the if the radius of the solid cylinder is capital R? What is the length which touches the liquid surface? 2 phi R. Then I can say that F equals 2 phi R into capital T. Total surface tension force acting on the solid cylinder is vertical downwards. Magnitude is 2 phi R, simple T. Right? If there's a hollow cylinder, suppose if there's a hollow cylinder, in this case, surface tension forces now. In this case, what is the total length of the hollow cylinder which touches the liquid surface? External perimeter, if I say external radius is R1, internal radius as R2, then there will be surface tension forces exerted along the external circumference of the hollow cylinder, and also internally, because this inside also there is water liquid, then there will be a length of the solid which touches the liquid inside also. Then the total length of the solid which touches the liquid surface will be 2 phi R1 plus 2 phi R2 into capital T. That's the idea. I hope you guys understand what could happen when the angle of contact is 0, how to find the resultant surface tension force acting on the solid. That part is done. Now case number 2. Now case number 2, if the angle of contact is acute, inside the bracket theta is less than 90. If the angle of contact is acute, that means theta is 90. Theta is less than 90. Hereafter, I only explain considering this rectangular object, right? But you want to understand how would be the resultant surface tension force in other these two geometries as well. I hope you understand, right? I explained what would happen now. Case number one, when angle of contact is zero, what is the conclusion? Result, when the angle of contact is zero, what is the direction of surface tension acting on the solid? Vertical downwards, right? This is the surface tension acting on the solid. If I ask you surface tension acting on the liquid, vertically upwards. But I'm talking about surface tension acting on the solid. If the angle of contact is zero, what can you say about the surface tension acting vertically downwards on the solid, right? How do you find the, suppose if you immerse partially, if you just dip different objects with different geometries, how do you find the resultant surface tension acting on the solid, resultant surface tension force acting on those geometries? I told you that always find the length of the solid which touches the liquid surface. Always find the length of the solid which touches the liquid surface. If the angle of contact is zero, multiply by capital T. If the angle of contact is zero, find the length of the solid which touches the liquid surface. If the angle is zero, multiply by capital T. Then you will obtain the resultant surface tension force acting on the solids. Usually they are vertical downward direction. Okay. Now case number two, angle of contact is acute inside the bracket theta less than 90. Theta less than 90. In that case, what would we do? In that case, I raise the board. Now less than 90 is the idea, less than 90, because this angle is less than 90. This theta is less than 90. This type of scenario. So if I raise this, if I draw it for your understanding, the same rectangular object, I try maximum to draw properly. Right. Now angle of contact is less than 90, acute angle. Then how would be this liquid surface? How would be this liquid surface? This liquid surface would be right. I think you guys getting some kind of idea now. When someone is looking from this side, okay. So when someone is looking from this side, this is liquid, right? This is liquid, right? All this region is covered by the liquid. When someone is looking from this side, he sees a wave in this way, right? Just think about this side. Then liquid is in the shape of concave shape. Concave shape. What is the direction of surface tension on the solid? What is the direction of surface tension on the solid? Downwards. If I mark those surface tension forces, if I mark those surface tension forces, if I mark them, then diagram is not clear. This is how they appears. So don't worry, I will draw the front view also, then you will understand. Okay. If I consider liquid surface like this, if I mark the surface tension, if I mark it, it will be like this. If I draw the front view, then you will get understand much better. Now I can resolve. Now, if I resolve now, this is somewhat inclined. So if I do the front view, if I resolve it, you will understand. This is the perimeter which touches the liquid surface. This is the perimeter which touches the liquid surface. So if I resolve it, now you'll understand. Now along the length of the solid which touches the liquid surface, there will be surface tension acting on it. Right? If I resolve the surface tension into two perpendicular components, one is always vertical downwards. If you carefully look what I have drawn, if I resolve the surface tension, one will be, now if I split this one, if I resolve this one surface tension component will be acting vertical downwards, T cos theta. Right? One surface tension component will be perpendicular to the solid surface, away from the solid. Perpendicular to the solid surface, away from the solid surface. That is T sine theta. T sine theta. I say blue color is T cos theta, and I say blue color is T sine theta, and black color is T cos theta. Black color is T cos theta. In that case, along this perimeter of the solid, there will be surface tension forces acting this way. Black color T cos theta components. T cos theta components. Okay. And blue color T sine theta components, always T sine theta components perpendicular to the solid, away from the solid. This blue color components will be perpendicular, away from the solid. Then you will understand what can you say about the resultant surface tension force. Just think about this blue color T sine theta components. This blue color T sine theta components get cancelled out, right? This blue color T sine theta components get cancelled out, right? All the blue color T sine theta surface tension components will be cancelled out. Therefore, there will be resultant surface tension vertical down direction. So if I ask you that, what is the length of the solid? What is the perimeter of the solid which touches the surface of the liquid? 2A plus 2B. If I ask you that, what is the resultant surface tension? Because surface tension is capital T, but when you resolve it, we get T cos theta, T sine theta. Along the perimeter of the solid, all the T sine theta components will get cancelled out. So therefore, there will be a resultant T cos theta surface tension acting down direction. Do you understand? So therefore, what is the resultant surface tension force acting on the solid when the angle of contact is an acute angle less than 90? T cos theta into the perimeter. T cos theta into the perimeter. 2A plus 2B into the T cos theta. Therefore, resultant. resolve vertical down, F equals what? T cos theta into the perimeter 2 simple A plus 2 simple B. Then case number 3, then based on that, I think T cos theta, even for the next 2 example also, even you dip a solid cylinder or hollow cylinder into this liquid, if the angle of contact of the liquid is less than 90, then always your resultant surface tension force acting on the objects would be T cos theta into the perimeter, if not length of the solid, which touches the solid's liquid surface. Right? That idea is done. So then case number 3, when the angle of contact is obtuse, that means theta is larger than 90. When the angle of contact is obtuse, theta is larger than 90. Theta is larger than 90. Right? Theta is larger than 90. Now, in this case, now what will happen? Now, theta is larger than 90. Okay. If I do the diagram roughly, yeah, if I do the diagram roughly, if I draw it, in this case, obtuse angle means you want to understand convex meniscus, right? Convex. Then if you draw a tangent line, if you draw a tangent line, if you draw a tangent line, this is liquid. This is liquid. If I measure angle of contact from the solid to the tangent line, from the solid to the tangent line, to the liquid, to the liquid. Okay. What is the direction of surface tension acting on the solid? Direction of surface tension acting on the solid? Direction of surface tension acting on the solid is upwards, capital T. This is the important thing that you want to understand. Important thing that you want to understand is, if the angle of contact is obtuse, direction of surface tension acting on the solid will be like this. Because surface tension acting on the liquid will be this direction. This capital T is surface tension acting on the liquid. Because why? It seems like someone is pushing this liquid this side. Someone is pushing, stretching this liquid this direction. So therefore, direction of surface tension acting on the solid will be opposite. This is the surface tension acting on the solid. If I resolve it now, in this case, I will say this angle is alpha. Theta, this angle is alpha. If I resolve it, I will get that. Vertically upward surface tension component will be T cos alpha. Right? Horizontally away component will be T sin alpha. T sin alpha. Then if I try to draw the liquid, it would be like this. It would be, right? It would be like this. Am I correct? So liquid. Then the surface tension forces would be, surface tension would be this way. It's coming upwards. Difficult to draw it. It's coming upwards. It's coming upwards. Okay. In the cross, there's some kind of side wave is drew here. You can get the idea. Again, if I consider only the perimeter and if I mark the resolved surface tension components, if I mark the resolved surface tension components, that you will notice that. You will notice that. Then D cos alpha surface tension components are acting upwards. Acting upwards. That T cos alpha components acting upwards. T sin alpha components are acting perpendicular to the solid, away from the solid. If I ask you the resultant surface tension force acting horizontal, that's 0. Am I correct? Resultant surface tension acting horizontal, 0. If I ask you what is the direction of resultant surface tension force, what is the direction of resultant surface tension force acting on the solid? Vertically upwards. Do you understand? That is T cos alpha. I hope you understand. Then how do you find the now that rectangular object length of the perimeter which touches the liquid surface is 2 simple A plus 2 simple B. How do you find the resultant surface tension force acting on that object? Perimeter into T cos alpha. You got what I'm saying? That's the idea, the summary. If the angle of contact is 0, direction of surface tension vertically downwards. Okay. Resultant surface tension also vertical downwards. If the angle of contact is an acute angle, less than 9 degree, then surface tension, resultant surface tension component will be T. Its T resultant surface tension component would be T cos theta. T cos theta vertical downward direction. Resultant surface tension force also acting vertical downward direction. If the angle of contact is obtuse, resultant surface tension component will be T cos alpha upwards. Resultant surface tension force acting on that object also in upward direction. That's the important thing that you want to learn. Okay. I hope you guys understood up to now. Everything is very clear. Right. Okay. The last I explained about surface energy. That knowledge. Right. Okay. Right. Give me a second. Give me a second. Now put your main topic, excess pressure inside a spherical meniscus. Put your main topic, excess pressure inside a spherical meniscus. Main topic. Somehow we'll finish the theory as soon as possible. Main topic, excess pressure inside a spherical meniscus. Right. Now, very careful listen. Now, just think about air bubble trapped inside a liquid. Just think about air bubble trapped inside the water. Right. If I draw that, if I draw it, now I'm talking about excess pressure, you will understand what does it mean by excess pressure. You will understand. Okay. Yes. Yes. Now just think about, now there is an air bubble trapped inside liquid. There's an air bubble trapped inside liquid. Mm, it seems like okay, right. Okay. Air bubble surrounded by liquid, any liquid, right? So liquid. It's an air bubble inside a liquid. What's my goal? I'm going to find an expression for excess pressure. I'm going to find an expression for excess pressure. Now let's assume that now in hydrostatics we learned that with the depth of the liquid, total pressure of the liquid particles changes. But in this case, we'll assume that pressure produced by the liquid always a constant. If I say pressure produced by the liquid as, if I say pressure produced by the liquid as P1, pressure produced by the liquid, pressure at any point in the liquid, pressure at any point in the liquid, if I say P1, P1, P1. And also pressure inside the air bubble, if I say P2, any point in the air bubble, if the pressure at any point inside the air bubble as P2, P2, right? Then we know what is the pressure, because when pressure acting on a surface, there will be pressure forces. Because force per unit area is we defined as pressure. If pressure is acting along a surface, there will be pressure forces perpendicular to the surface. Do you understand? If pressure acting on a surface, there will be pressure forces acting perpendicular to the surface. In that idea, right, you will understand that. Think it's a sphere. Think it's a sphere. Then pressure produced by the liquid, right? Because of the pressure of liquid, liquid produces pressure forces. Liquid produces pressure forces on this air bubble, perpendicular to the bubble surface, all the directions, liquid produces some kind of pressure force perpendicular to the liquid surface. I hope you understand what I'm saying. If I ask you what is the resultant force produced by the liquid on the air bubble, due to the liquid pressure, what is the resultant force produced by liquid on the air bubble? What would be your answer? Your answer would be 0. Because why? All the directions this liquid produces force perpendicular to this what? Bubble surface. As a result, resultant force acting on the air bubble would be 0. Very similar manner, pressure inside the air bubble. What is the resultant force acting? Because of the pressure inside the bubble also, there will be some kind of pressure forces acting inside the bubble in all directions. If I ask you what is the resultant force acting inside the bubble due to the pressure P2, again result will be 0. Result will be 0. Right? Result will be 0. If I take half of this sphere, if I take half of this air bubble, if I mark the forces, very carefully understand. If I consider half of this air bubble, and if we mark the forces, right? Very carefully understand. If I consider half of the air bubble and if I mark the forces produced due to the external pressure P1 and forces produced due to the inside pressure P2 on this half of the bubble, right? Resultant pressure force acting on the half of the bubble due to the liquid pressure will be horizontal direction. Because just think about half of a bubble. If you think about half of the bubble, if you think about half of this bubble, understand, but think it's a half of a sphere. So when you think this half the sphere, pressure forces acting perpendicular to the bubble surface in all the directions. Pressure forces act perpendicular to the bubble surface in all directions. If you obtain the resultant pressure force acting on this half of the bubble due to the external pressure P1, resultant would be, I say F1, always horizontal right side direction. Resultant would be horizontal direction right side. So very similar manner, due to the pressure inside the bubble also, there will be pressure forces acting, what? Perpendicular to the surface of the bubble in all the directions. What is the direction of resultant pressure force acting on this air bubble due to the internal pressure P2? Horizontally left. I say F2. In addition to these two pressure forces, if I consider half of this air bubble, due to the liquid pressure, there will be resultant pressure force acting on this half of the bubble in the horizontal direction. Okay. And also there will be resultant horizontal force acting on this half of the bubble to the right side direction due to the inside pressure P2. In addition to this F1 and F2, as the surface of this bubble is stretched, there will be surface tension forces acting acting along this perimeter also. If I find the resultant surface tension force acting, if I find the resultant surface tension force acting on this half of the bubble, it will be how much? What is the length of the half of the bubble at which surface tension forces are acting? If I say radius is simple r, radius of the bubble is simple r, radius of the bubble is simple r, what is the resultant surface tension force acting on this half of the bubble? That is also to the right side direction. How much? Right side direction, 2 phi simple r into simple t. 2 phi simple r into capital T. 2 phi simple r into capital T. Result is surface tension force 2 phi simple r into capital T. What is F1? F1 means understand. Pressure means force over area. Force means pressure into area. Pressure is P1. Now, what is the area? Now, when I consider half of this air bubble, what is the effective area? What is the effective area on which these pressure forces are acted? If I ask you what is the area, if I take this half of the sphere, what is the area on which pressure forces are acted? Then your answer would be surface area of a sphere is 4 pi r squared. Half of a sphere means 2 pi r squared. If I ask you what is the effective area on which these pressure forces are acted, your answer must be 5 r squared. Why? Because when you resolve all these forces through this half of the air bubble, the resultant force component will be acting horizontally. Now, if you resolve all these pressure forces, the resultant pressure force component will be acting horizontal direction. Then the effective area would be this cross-sectional area of this air bubble, 5 r squared. So therefore, P1 into 5 r squared. Very similar manner, F2 also will be P2 into 5 r squared. 5 r squared. If I consider the equilibrium of the air bubble, what can I say? F1 and 2 phi RT. F1 plus 2 phi R simple T must be equal to F2. F1 means we know that P1 into 5 R squared plus 2 phi R simple T. F2 will be P2 into 5 R squared. Then when you simplify this, you will obtain, if I divide 5, all the simple R cancel out, then I am getting P2 minus P1 simple R equals 2T. Therefore, P2 minus P1 equals 2T over simple R. It's an important equation you must learn by heart, right? Then always understand pressure inside the bubble P2 is larger than the pressure outside the bubble. Important idea. I think up to now everything is very clear. Yes, right.